I have 5 second points for this one.
Okay, I genuinely don't know what problem it is. So thank you.
Problem A, you're given like a bunch of people, and they each have a score and a handicap, and so their total score that they end up with is just their score minus the handicap, right? So what you do is you scan them all in, and for each person, you take the handicap away from the score, put it like in an array or something, and you just sort it and output it. Okay. Something that can catch people is that they want the output. For ties, you output the people in the order they're given in the input. Okay, so just call me. But like anyway, so like what you do is you also store the indices that the people show up in the input, and then sort of that, and it will just work.
What's the other solution?
There is another solution.
Yeah, it's SCD sample sort.
Yeah, sure. Like I swear I tried that, didn't I? No, the second time we tried was you were like change the sort to a stable sort. Submit it.
No, it's only sorted by the name afterwards as well. So it didn't change.
No, it didn't. You need a constraint.
Because you had a pair of the pair store their name. So stable sort didn't help because it's all by name.
I just sorted by first.
So apparently, like we don't like.
Okay, anyway. Sure. Okay, so that was problem A. I don't think there's much questions for that. Problem B. So you're given a bunch of items or the costs of items that you buy, and you're given the total amount of money that you have, and you want to calculate the total price it will cost, the rounded price, so the price you actually pay if you give cash, and also the change that you'll be given after you buy those amount of items. So like all you have to do is just add them together for the total price. When you round it, okay, this catches people as well. But apparently in New Zealand, they don't have 5-cent coins. So you round it to the nearest 10 cents instead of the nearest 5 cents. So we cop the penalty for that. But okay, so yeah, so for total price, you add them all up. For rounded price, what we did was we times the 100 to change them all to cents. We divided it by 10, rounded it, and then times it back by 10, and then divided back to 100. Change it back.
That out.
Combine two. Like, what will I do? So if it was 49.21, I will times 100. So give me 4921. I will divide it by 10. So I end up with 492. And then I will times it by 10, so I get 4920. And I'll divide it by 100, and it would give me 49.2.
My old class is like my first pair.
Like this, round.
Why did you divide by 100 like integer divide or like
Float. It's float division.
and you want float to be?
Because it's
Why don't you just print like formatted print for like cents divided by 100 point cents and just stick a cent mod on it?
Even more about the divide by.
Sure. Like this is just clearer to think about.
Yeah, fine, I guess. But like, surely do you not run into float problems because like 100 is not like binary enough?
It's close. It's accurate.
No, you do truncate the answer.
Yeah, okay, fine.
So it's like fine.
Okay, cool.
But you round it to 2 decimals.
That's why.
Because
Yeah, I
everything
think
is
that's
Good enough.
This is why we use printf .2d.
If you wanted to do it like perfectly precisely with no chance of error, number of cents divided by 100, like integer divided by 100, and then print it, and then number of cents mod 1.
Yeah.
If you look at, because it's a website.
So yeah, that was problem B. So I think it's quite difficult. You have to notice that the smallest denomination is 10 cents. Ridiculous. Anyway,
I didn't know that problem.
in problem C, what you're given is a like I'm trying to put windows or something. And you're given like the dimensions of the wall, which is like H by W, and you're given a bunch of windows, and you have the dimensions of the windows. And what the question wanted is how much space will be left after you tile the windows, and you are also to check whether you run out of. So like if you don't have a wall after you put all the windows in, they also don't like that because they still want some wall, right? after they put the window in. So if you end up with, okay, if the entire wall is covered by windows, or if there's more windows, okay, or if there's like windows jutting out after you cover the entire wall, they want you to output, please check the dimensions. Otherwise, like output whatever's left of the wall in square meters, right?
And the windows be overlapping? Each other?
No, they can't overlap. Okay, so okay, two things about this problem. So they want you to output it in square meters, and they give it to you in millimeters for some reason. So,
I wonder if
so that was an issue with this problem.
No,
What other issue do we have this? Yes, also sample output one was also wrong. It's 7.32 instead of 7.31. And other than that, it was like fine, I think. Like I did all my calculations in integers, and you just divide by 1,000,000 at the end to convert, and then change it to floats. And it just works. Okay. Problem D. Okay. Column D was the thing where like you can read the word just by looking at the first and last letters, and like the middle letters can be jumbled up, and it turns out that you can still read it perfectly fine. So what it does is it gives you a bunch of sentences, and for each word in the sentence, if the length is bigger than or equal to 4, they want you to reverse the letters that aren't the first letter and the last letter. So reverse everything in the middle. So like your word becomes WROD, and like apple becomes like ALPPE. Right. So they want you to do that. Yeah, so pretty straightforward. I think the annoying thing about this problem is that the input isn't very nice. Like they don't give you how many words are in the sentence. So you have to, well, we use Python for this. And like, yeah, just import it to the line and then dot split.
Yeah.
And then reverse the line.
Does anyone want to talk about the C or C++ ways of doing this?
You can like get a line and then like delimit.
Yeah, you can do get line with a delimiter. The other way is get line and then string stream.
Yeah.
So you put them all onto, like put the entire line onto a string stream and then read tokens.
That's a very bad way.
Oh, okay. But anyway, it would have been really convenient if they just provided how many words are in the sentence, right? So, like,
I agree.
But it adds to the difficulty, I guess. Okay. Okay, so that was problem D. Problem E was like you had a bunch of students, and they got slapped with a bunch of penalties. And so like based off the code, each code maps to a specific amount of penalty points. And so like you just wanted to check for particular students whether they had more than 30 and less than 50, or whether they just had more than 50. Right. So you wanted to print the student, or to print the names of students who had a score of 30 to 50, exclusive, inclusive, and print the students who had a score just bigger than 50, bigger than or equal to 50. No, bigger than 50. Yes. And the way you do that is like you just take your code and you slap it in a map, right? That maps your code to the number of points. And then when you go through the students in the input, you just add the mapped points to that student's like code. And then at the end, you just do one loop to check whether they're or which category they fall into. I think what else was annoying about this problem?
Order again.
Did they want order?
Yeah.
Yeah. So they wanted it in input order again. Yeah, they wanted it in input order. And the way I did that was when I read them in, I put them into a vector. And then like they could also have duplicates. So like, yeah, like it wasn't very good, but like it passes. So like I put them into a vector, and to check whether I put them into a vector or not, I have a set of them that can check whether I have put them into the vector or not. And then at the end, you just loop that vector, and it gives you them in input order. Like, sorry.
I did that as well.
Yeah. I'm like input order is like I don't know, not very nice. But okay. That was E. And F. Like how did F work? So F. That was relatively straightforward. They wanted you to print some stuff. Print like a graph or something. And like all you have to do was they gave you the input by characters, and they gave you the positions where each character had to go. So like, you create a 2D grid, 2D array at the start with dimensions that they give you, and for each character, just put it into the position that they give you for it, and at the end, just print it. It's like pretty straightforward, right? What was annoying about this problem? Oh yeah, they give it to you in X, Y, so it's column row instead of row column. So yeah, you just like that's how you insert them into your grid, I guess. Okay, so I was like F, and I didn't do G. I want to talk about G. What was G? 7 wonders.
G is okay, like G, you're playing this game, the time people score, and they give you like 7 tricks just to like read and make sure you understand. So you're given a bunch of players, then their names, and the way it works is that people have points and coins, and so like a bunch of things happen. So the first thing, I'm not bother drawing it. The first thing, they give you like a number for everyone, just add the points. Then the next thing they do, they give you some number in like a weird format, like W number, 1 number, followed by X, 1 number, then Y, 1 number, then Z, then 1 number. And like this one's worth 1 point, 3.5, and -1. So just like read in the word and I just add it up for each person. And then the next 2 lines are just like points for each person. You just add to their point total. Then the last one is like AN. And the last existing one is AN, BN, BN. So what you do is you add up each of these numbers, and then you add on 8 times the minimum of each of these numbers. That's how the game works, I guess. And then the last one is they give you the coins for each person. You add on like more points divided by 3 for each person. And so like if you didn't read the question wrong, you should have the points for every person and the coins for every person. And you just print out. Every person's points. So like it's like a bit. I liked better wrong. I thought they would just sort it. It's not like exactly clear, but it lost like 2 penalties on that. But they want you to print out their scores in the input order. And then at the end, you'll print out all the people with the maximum points. If they're the same, then it's the maximum points. And for those with the same like number of maximum points and coins, you should print them in input order. And you may make sure you write winners instead of winner. It's like multiple. And so like if you just make a mistake, like you just do what they tell you. Like I think there's much to say about that. It's like easier in Python, I think, than C++. H.
Okay, H was a somewhat messy input and output problem. So you're given a list of you're given a game of darts at a list of where the thing hits, ignoring bullseyes, and you have to work out if someone wins or if not, then how much score is left. And the way scoring works is that each round, if someone gets to exactly 501, then they win. Otherwise, if they go above 501, or if they get like 500, or if they get 501, but their last thing wasn't a ×2, then they don't win. And it seems really case-bashy. It actually becomes less case-bashy than you think. So the input format is kind of annoying because they don't actually tell you how many lines you need to read in. So you need to read in a bunch of lines with 3 strings and then detect when one of them ends in 1 string. I ended up just because I didn't care about efficiency, you could just have a function that returns a vector of strings for each line. And then you just manually check if it's the end. Otherwise you know that it's going to be the score. And so then for parsing each score, there are actually just 3 cases you need to consider. If it's X or 0, you just skip it. Otherwise, you have to deal with some multiplier, which will be in the first character, and then some number. For instance, if you had T20, this would be triple 20. So checking the first character, you can just do it with a like if else statements, or getting the number and turning that into a number. It's annoying because we've got this character at the front, but you can just use the good old C function stir tool. You have like stop stir +1, where +1 just is the first character. And then just, paste. And yeah, my code for this ended up just like having a pair of pointers for the two players in order to like swap easily. But it turns out not to have too many cases. The next problem is another problem with a bunch of annoying cases. So in this problem, you have a pair of robots next to a conveyor belt. The conveyor belt has 100 slots, and there's one robot on each side of the conveyor belt. They're named and on each turn, each robot can do one action, which is either move one space to the left or right, stay still, or deposit an item from their current slot onto the conveyor belt. You can't have multiple robots depositing an item onto the conveyor belt at the same time, which actually wasn't mentioned in the problem statement, but you can infer it from the explanation for sample input 1. And so you're given some ordering of which items must be pushed onto the conveyor belt at each time. So the way I end up implementing it is you just have 3 queues. You have a queue for items of B, a queue for items of O, and then a queue for which robot leads, like the order of the 2 queues. And then you could try to do something fancy where, like, you check over each item, you figure out what distance each robot needs to move, and you add that. But then you would have so many cases to deal with. What you can instead do is just a really inelegant solution where, like, each step you just calculate which direction each robot moves. And I'm not sure if they ever actually give me strength, but like it's only 100 long, so it won't take that long to just simulate it. And it ends up being fine. You just have to deal with a bunch of really annoying edge cases.
As a word.
I think a lot of this will just next is K, which is like
Otherwise, we could have also done that.
it's the one I can around.
Yeah, but I think the other one, else is
What was I? And it's the one where like the sheet says like different ingredients. Like what's given in the statement. And so for this one, it's the same set of words twice. So there's only like a few combinations of like things you can say, like either you say A, B, A, B, A, C, B, C, or A, B, C. And so like since the like only a few things, you can just like write any brute force to calculate. Just the best thing to do for everything. But they don't tell you like the number of days there are or like the bounds. So what I did was I pre-calculated the answer for like because you can't use more than 4. Can't use more than 4 or one of like the words. So you just pre-calculate like the answer for every combination of like numbers from like 0 to 4. like 125 cases. I just brute force every permutation that you might want to do these in and see how many it does. And like that's fast, pretty fast to do at the start. Then you add to every field query, like some of the time. It's looking at like, if you can't read in this import fast, there's like no solution. If that works, then like as well. Just do it.
There's a more elegant reading where you just like try them all in dash order. Dash order always being
Oh yes.
except possibly twos.
You might have stopped one of these, but like I just did them in like I just like did every permutation. So yeah. What's that?
Yeah.
Oh. Okay. Yeah, we're trying. Well, so for K, you have a 4x4 binary grid. Kind of rotate it 90 degrees clockwise. And so for this one, and note that it's only like 4x4. So it's only like 16 different numbers. Yeah. And so there's only 2 to the power of like only 2 to the power of 16 different possible like configurations of the grid. Which is like around 50,000, which is like not many, like maybe like 70.
When you do the shape.
And so for this one, so for this one, let's do a BFS on every possible grid state. So for some grid, like the edges are you rotate it, you flip a row, you flip a column, like you just implement that with a BFS, and you set the answer. If you've done BFS on like not just a normal graph, then like you can just do it.
Don't know when to apply.
Anyone does anyone get that? Yeah. Do a BFS on the grid. Like the way that I implemented it was like instead of like a 4x4 grid, right? Like no, it's like really small. Instead of a 4x4 grid, just turn it into like an array, like an array of like 16 things, right? 16 bits. It's just like top to like left to right to the bottom. And you can store this in like as a bit mask of an int, right? So I just make a scene array of size like 1 to the power of 1 to the power of 16. I'm sorry, 2 to the power of 16, not 1 to the power of 16.
Yeah.
You make it like an array of 2 to the power of 16, and you just store your grid in that. And so you can pre-calculate like the 8-bit mask that correspond to like if you XOR it with the int. Like some bit mask will correspond to flipping a row in a column, and you just manually write the rotate by like rotate 90 degrees. Like each cell ij goes to j n minus 1 minus 5. And like you just apply that to everything on the rotate. And then you just XOR with the appropriate bit mask to do the row flip. That's how I coded it for that. It's like quite fast.
All of them have like a grid. And you want at each intersection lives some amount of people. And you want to build a highway on this grid that starts from the top left city and goes to the bottom right city and only moves right and down. So like something like that. Something like that. And so like after building a particular highway, everyone living in this grid wants to use this highway. And so they will move to the highway. And when they move towards the highway, they can only move down or to the right. So for instance, this person will just move down to here, down to there. It's a terrible example. Or like, okay, this person will like move this way to meet the highway, and this person will like move that way to meet the highway. It doesn't go. They can only move right and down. It's hidden in like a fat paragraph in the problem statement. Like you only move right or down to the highway. And so which makes the problem like a whole lot easier. Like you can solve it with like DP, right?
Maybe they should
Like if I define DP RC to be like highway from 0, 0 to like RC, like, what's it called? Like, score or something. Like, score that's, contributed by people traveling to the highway. 0, 0 to RC. Then like, you think about like how it can transition, right? Like, if I'm calculating like the DP value in this cell, so that one's RC. So then the highway can like come from the cell above it or the cell from towards its left. And so like if it comes from the or if the highway comes from the cell above it, then the only people that you have to consider the inconvenience for is the people to the left of like the cell that you currently build your highway to, right? And like, so that is if you that's if you transition your highway from the cell above you. And if you transition the highway from the cell to the left of you, it's like a similar story. Like if this was RC and the highway looked like this, then you only have to consider the inconvenience of the people in the column like above you. And like you don't even have to like compute these like fast because n was less than or equal to 100, right? Like you can just loop through and like calculate what the inconvenience of the people in a particular row to the left of you or in the column above you is. And like it just works. And your answer is just DPN. I think there's much else to say about that. But yeah. They don't give constraints on like how many people live in a particular spot as well. So I just use longs and hope. And did it say that? Just slap the long and hope for the best.
Oh, they use the call for that.
Yeah, that makes 10 people.
Oh, okay. Well, so that's like, well, yeah. I mean, like, it's fine.
At most 10 people.
Okay. Now it's like
Okay, the next problem is an interesting one. So we have some which has a bunch of islands in like groups. Okay, and the weather god wants to place a bunch of instances, I guess, so that they can reach every island. So you want to select some number of points, and at each point you select, you can see all of the islands on the same row and the same column. So I can place a point there to see those 4 islands, there to see those 4 islands, and there to see those 2. And you want to find the minimum number of points such that you can see every island on the map. So one interesting observation to take is that you never want to place the instances on the same row. We can do this in a argument. So if we have 2 people on the same row, they will cover that row and both of those columns. If we move one of them to the same column but an unoccupied row, then that row and that column will still remain seen, but we will have one extra row seen. So the new thing seen will be a superset of the old thing seen. So now that we know that we want to place at most one thing on each column, we can make another observation in that suppose we place a bunch of, suppose we are told magically which columns we want to place the wind creators in, then we don't care about the positions of the blocks in those columns because they're going to be seen by those things we're creating. So instead, we only care about the rows that contain things, not on the columns that we're already placing things in. And each of those rows must have at least one of the wind creators placed in it. So given which columns we're placing the wind creators in, we can check if it's a valid solution by counting the number of rows with at least one block got from one of those columns. At this point, it helps to read the problem very carefully, where it mentions the grid size is exactly 15 by 15, which means that we can just brute force over every combination of which columns we're placing things in, because that's just 2 to the 15, which is about 30,000. So once you've, for each thing that you're checking which columns you place them in, you just find all of the columns that do not contain a thing, take the bitwise OR of all of their rows of all of the items in them and check if you have enough things. And so that's where it really helps to use the GCC's built-in function, built-in pop count. So this is not part of the C standard library, but it's supported by GCC. I'm not sure if it's supported by Clang, but all the competitive programming contests use GCC anyway. And this returns the number of bits in X, which are set to 1. And yeah, that makes a bunch of the bitwise operators in this problem a lot easier, including getting the final answer.
C++20, there is pop count in the language set.
I have a question. Do you know what greedy doesn't work?
So the greedy I considered was just taking the like largest number of things each time. I didn't actually go into that much effort into disproving it once I realized that n is equal to 15. Do you have any greedies in mind?
How many boxes it can see? I don't know. It's further than that.
Yeah, the fact that n is equal to 15 is a hint that we want something exponential. I'm not sure. I spent like ages trying to find an n squared solution because I didn't read the problem. So like log 3 constraints carefully.
So for problem N, you want to count the number of sequences of numbers between, so given two numbers n and m, the number of sequences of length n, where every number is between 1 and m, and every number is a multiple of the previous one. So if it was like 3, 3, the example they give is like 1, 2, 2, that's fine. It's like times 2 times 1. Or like 1, okay, this thing's terrible. You can make 6, 5. You can have like 1, 2, 3, or like 2, 3. But like 2, 3, 6 wouldn't be bad because this here doesn't work. And so one solution you could try is like you define maybe DP of so the observation is that like you make the sequence for left to right. You only count the last number, and you can do like DPIJ, the number of like sequences of length I and end with J. But if you do this, the transition will be like, so mine's like n times m log m, which is a bit too big since both n and m are 10,000. So you can't quite do that.
Our solution was bad. It's about
It was fast enough.
Yeah.
But what?
We did the DP swap state, so it used ON.
Okay, well, you can solve it in order n m log m, but you can do like a lot better. But like I don't know what passing. How big is that? 10 to the 8. It's like 9 zeros. Huh? Yeah.
Oh, okay.
Okay, so you can do this in like 1.4 billion operations somehow. But you can do better than this. So, okay. Watch, I just tried it. I don't think like 5 seconds. Okay. So what you can do instead, right, is, for example, we have a sequence that's like one. Actually, no, I'll make it probably 2. We have a sequence that's like 2, 6, 12, 48, right? For example, this sequence. Or you can instead, you can think of it instead as like a bunch of, it's like an invisible one at the front. I can count, you can instead turn the sequence into like each number like divided by the previous one. So that becomes 2, 3, 2, right? And so I can see each of these, right? It's like a prefix product. You take a prefix product of this, you get like the top one, right? And so this is like the divider rate of the, I don't know. So like you find each number divided by previous one, and you'll count these sequences instead. And so by the same constraints as the problem, all of these numbers have to be like at least 1, and the product has to be less or equal to m. So we're counting the number of these arrays with a product that's looking at m. And so the observation here, right, is that if m is like, since n and m are all less or equal to 10,000, right? In the worst case, you can have like at most 13 like 2s in this array here. And so that makes it like a lot easier because like if you have 14 2s, right, the product would be over m. You'd like be too big. And so instead what we'll do is we'll like specifically count number of sequences that like don't include the 1 or like grab the ones afterwards. Because like you'll have most of it will be 1, and you'll have a few like non-numbers which are like more than 1. So instead you can do dp of ij because the number of sequences of length I product j such that every single number is at least 1. So like sorry, every number is at least 2. And so like this I, right? Like this is like that's what we put at 13 because you can't have a sequence length 14 with no 1s in it. And so with this DP, the transition becomes like DP of ij is just you just like you calculate all the factors of like j. And so like DP ij will be the sum of like all k that divides j, that's the notation. dp of I minus 1 like k. Wait, that's true. I think so. That's what I did. Yeah. And yeah, I think that's correct. You just like for each number, like the product is j, and so like all the previous numbers. Okay, yeah, I think it's like that. So this corresponds to putting like j over k at the end. With like k bigger than like k has to be bigger than 1. And so for this DP, the transition here, I think it adds up. For every single like length, the number of like transitions you do is like odd, I believe. The total number of factors over all the numbers up to m is like m log m. I think that's correct. And so this solution is order. Oh yeah. Okay, so far after you do this, right, you have a bunch of sequences of each length, multiply to j. And so what's left is put the 1s, right? And so this every single one of these sequences will be stars and bars with like number of 1s. So if you have like if n is like maybe like 5, and you have a sequence which is like 2, 3. We're gonna find the number of sequences of length n that have like 2, 3 in that order, with 1s everywhere else. And so kind of like And so, wait, so let's start at 1 actually. Like, you just pretend everything starts with a 1, right? And you just pick 2 of these to turn into 2 and 3, like this, right? Like 2 and 3. And so for each thing, right, you sum over all states, but for all I and j, you just add to the answer. It's just dp for all ij's, you add to the answer. dp of ij multiplied by like n of j, so n choose I. Yeah, n choose I. By n choose I. And so they calculate the factorials and inverse factorials. I think there's a way to do it in order n. Going factorial up to n. And then for this dp, it should be m log squared, I think. Yeah, I do it faster. Yes, right. I appreciate this problem. Next one. I think sweet.
So the next problem is problem O, where we are demolishing a swimming pool with very high quality occupational health and safety requirements. So the demolition company has decided to have some fun and make an enormous cascading demolition where the upper floors fall on top of the lower floors and demolish them. So in the sample input, we have a 5-story building. Each floor has a swimming pool, initially with 400. Okay, the sample input is very uniform, but these values can be different on each floor. So we've got 400 kilograms of water in each swimming pool, and each of these floors can hold 1,000 kilograms of water. If you demolish one floor, then that floor will collapse and the water will flow down to the lower floor, except each floor has some cost associated with it. So you want to find the minimum cost such that you end up demolishing the lowest floor. And the important observation to make is that you will only ever want to demolish some contiguous section of floors that includes the bottommost floor. Because if there is some floor that you don't demolish, then any floors that you demolish above it cannot impact the bottom floor, and so it would just be a waste of money. So now for every floor, we need to figure out how much extra water we would need to drop on it in order to demolish it. For instance, in this problem, if we have a floor that's currently supporting 400 kilograms of water and has a maximum capacity of 1,000 kilograms, we need to add an extra 600 kilograms onto it. And so then we can also calculate the total amount of water we would need to be dropping in order to demolish that floor. And that's just the amount of extra water we need to drop on it, plus the amount of water below it. So for instance, for this floor, we would need to drop an extra 600 kilograms on it, and we've got 800 kilograms below it. So as long as we are dropping at least 1,400 kilograms of water, then this floor will be demolished for free. And so we just create some sort of list containing for each floor the amount of water we would need to drop for that floor to be free and the cost of that floor, which in this case was $80. And now we can iterate up from the bottom to the top, storing at each point, if we were to demolish all of the floors from here down, how much would it cost? So we just keep a running total of the amount of water that we've seen and the total cost. And at each time we look at this array, which will contain more elements like we consider this once we've demolished 1,200, we save $200. So at each step, we check if there are any elements in this list where the amount of required water is less than the amount of water that we currently have in our suffix. And if so, we remove that from the list and subtract that cost from our running total cost. And then the minimum cost just becomes the minimum cost at each stage of the loop. And for removing things from this data structure and checking if anything is less than our current thing, you can use basically any data structure you can think of that will work with a set or a priority queue, a set tree. You could like sort them and put them in a linked list if you really wanted to. And yeah, basically everything will end up being O of n log n. And it will work fine if you either pre-compute this list at the start or add it as a running total, because these things will never interfere with the things below it, because the water cost will always be greater than the sum of all of the water below it because of how we constructed it.
Last problem is you have a graph and a bunch of elements. Like a town that I want to take your routes that goes from like town number 0 to town number. And each of these roads have some sort of like root point or something. And you want to make a specific order. All it's saying is that you want to find a path from 0 to 3, and they give you like a list of they give you like the list of ingredients, like 1, 1, 2. And so you want to take a path from 0 to 3, which uses like an edge labeled 1, an edge labeled 1, edge labeled 2. So here you can either go 0, 1, 0, 3, which goes 1, 1, 2, or 0, 2, 0, 3, which also is 1, 1, 2. In this case, you can, as a question asked, which towns like have a path that like goes through it that like follows these rules? So in this case, right, every time it's possible. But if I put like a fourth one here, like 2 or something, then you can't do this, right? Because you only get the 4 on the last day. But you need to end at 3. That's just not possible. And so for this one, like the bounds are like, and it's like 100. Yeah, the bounds are pretty small, and so you can write something like kind of like a DP. Do like a DFS if you wanted. Here DP of like TU equals whether you can reach town U at time t. Right. So the idea is that if you can reach like town 1, for example, at time 1, then since there's an edge, right, from 1 to 0, and they expect you to use an edge of like label 1 for the second thing, then if you can reach town 1 at time 1, so this is like time 0, right? Time 1, this is time 2, and this is time 3. If you can reach town 1 at time 1, you reach town 0 at time 2, right? Just take the edge and get it here. And so you can calculate all of these in like n cubed. Which town you see, which do you go to? Just like update the values. And so all n cubed you can calculate like n squared times t. But like T is the same. T is like really well. So you just do that. You figure out which towns you can reach at which point in time. But then afterwards, right, you make sure you end at so if you don't have to end at the last town, you can just check which nodes you ever worked on, and that would be your answer. You need to end at town 3 as well. And so you can just do it, you can do it backwards. I don't know, like reverse DP. Like the same thing, right? It kind of go backwards, like you retrace your path from 3 to 0 while using these like labels in reverse order. And so you check essentially each time which towns are able to reach the endpoint. And so if at some time you can, so at some time and some town, you can get there from the start and get to the end after. It's possible to be in a path. So you calculate this one with like the same thing but backwards in order and spread T. And then you just loop through all the times and positions. So you just loop through all the times and positions and see which ones like and if it exists in both, like forward and backward, then it means you can reach there. And so that's my solution. Just loop through all the time and towns and you can see which ones are like allowed. I guess you can also like store like which towns you came from in this part, like retrace it, but it's a bit annoying. Doing it twice is like easier. I think another approach, so you do like a state explosion where like each node has like a time associated with it as well. It's like the same solution basically. Yeah.
Cool. All right, thank you, everyone. That is our last SPAR round for this year. I just wanted to reiterate this was a mirror of the New Zealand programming contest, so thank you to the jury of the New Zealand programming contest for putting together these problems. At the end of each SPAR, you will have seen if you refresh the scoreboard more than a couple of minutes after the end that medals were assigned to like roughly the top 1/12, 1/4, 1/2, etc. And so for like multiple good performances over the course of the year, you will get certificates at some point when I get time to actually send those out, but those will be coming. The other thing that I need to talk about is South Pacific ICPC. So this is all training for the ICPC, the International Collegiate Programming Contest. This is the world's biggest programming contest for universities. Others are welcome to take part unofficially, that is ineligible for like further qualification, but yeah. So this is a team contest, teams of exactly 3, which will be held on Sunday, the 14th of September. Just like SPAR, it's at many sites across Australia and New Zealand. And so this first step is the preliminary contest, by which we select the teams which will advance to the next step of regional finals, where people come to here, which is where we host the regional finals. So hopefully all of you and many more will register for the preliminary contest, and we'll see you on the 14th, which is the day before term 3 starts, basically. The registration process is coming very, very soon, probably as soon as like tomorrow. Yeah, so you'll be making an account on a new platform that we have, and yeah, there's a lot of platforms, but yeah, you'll need to make an account on a new platform that we have that will allow you to either send a code to your friends to join your same team, or to let us make a team. Cool. But yeah, keep an eye out for emails. Every platform, everyone.
I need to teleport me. Name.
Oh, and IOIP. That's the forecast. Nice if possible.